Okay, stats kids. I'm not here today. I have meetings today, but we're going to continue on 5-1 notes. We won't finish them today, but we'll get, uh, you know, a little bit further along. I want to get to, let's see, right before part 2. So I'm going to get through example 5. So about a page and a half, 2 pages of notes, I guess, for right now. And yeah, we'll do that. We just got done talking about probability distributions, and it's talking about like the combinations that you can have for 2 different categories. So 2 different categories are boy girl. I could have a 4-0 if I'm having 4 children. I could have a 4-0 combination, 3-1, 2-2, 1-3, 0-4, and then our probability distribution labels on the right column what the probability is of that happening. Okay, right, for this table we were looking at a 50-50 chance, boy and girl, but as we move on we will get to things that are not a 50-50 chance. Like the chances of rolling a 2. So you could have a probability table that's rolling a 2 versus not rolling a 2. And have a rolling a 2 would be a 1 out of 6 chance of happening. And so your split would not be 50-50. It would be like a sixth or point. I think a sixth is 0.16 repeating or something like that. Anyway, you can have probabilities that are not 50-50, and we'll look at those closer, okay? We're going to break down some probability tables over here on this side. Ignore this formula. You can cross him off for now. We're not going to talk about him yet until like the next section. So ignore that formula up there at the top. But I do want to talk about this notation for 0 plus, okay? When we talk about a probability that has a very, very, very small chance of happening, like let's say the probability of something occurring is 0.000001. Like we had before, we had the chances of getting struck by lightning, or I think it was the chances of winning something in the lottery you guys had to do on your homework assignment, and you found out that there was a higher chance of getting struck by lightning than that happening. Okay, it was a really, really, really small number. Okay, rather than rounding that off, like this number would round to like 0 if you rounded down to the nearest whole number. But if you put 0 as the probability, then that means it's impossible. It's not going to happen, right? So the notation that we want to use instead is, instead of writing this number, if you want to not write 0.00000001, however many zeros, you can say 0 plus, okay? And by writing it as that means it's really close to 0, but it's not impossible. Like it's not impossible that it will happen. Impossible would be 0 exactly, but 0 plus means like slightly above 0, but like really not a good chance of it happening, okay? So if you ever have a decimal number that's really, really, really small and lots of zeros on the end of it or on the beginning of it, you can go ahead and write that as 0 plus. I would say if there's like more than 5 zeros, you could just put 0 plus in that spot and call it that, okay? So we'll revisit that notation for 0 plus again at some point, but I just want to kind of introduce it right now. Example 2 talks about this probability table, okay? And normally we say, like I said before, that a probability distribution table should not have categories, but for some reason they're trying to do one where it has categories. And these are mistakes that job applicants make during an interview. So they say 50% of the time they were making a mistake for inappropriate attire, so not wearing the right thing. 44% of them were late to their interview. How does that even happen? 33%. I would think that this was probably the highest category. Lack of eye contact. That's probably one thing that I've seen the most in interviews, like me interviewing other people, is lack of eye contact because people want to look down. So I would imagine that this would probably be the highest category, but they say 33%. And then checking your phone or texting during an interview. Like, how is that even a thing? I don't even know. But anyway, they have these numbers written down. And they say, does this table describe a probability distribution? Okay. Very first thing you want to check on a probability is like, do they add up to be 100%? Well, this is adding up to be 1.57, which is 157%. And so what's probably happening here is that some of the people who are flagged as having inappropriate attire are maybe also late to the interview. Like there's probably some overlap between those those two, and that's why we get 157%, but that wouldn't be representative of a probability distribution. So it says, does this table describe a probability distribution? No. Over 100% for my probability. So not going to be a good probability, not a probability distribution at all. Okay. All right. Now we're going to go to a legit one where this does add up to be 100%. And we're talking about tossing 2 coins. Okay. So remember, 2 coins, we could get a heads, a heads, tails, a tails, heads, or a tails, tails. So, and we're talking about the number of heads. So getting 0 heads, that would be the combination tails, tails. And that has a 25% chance of happening. Getting 1 head, that could be a head, tail, or a tail, head. That has a 50% chance of happening because that's 2 combinations out of 4. Okay, a double heads would be a 25% chance. So this is how this table is broken down. They want us to find the average or the mean number of heads, right? So there's a formula for this, and they want us to do, so the formula, let's break this down. This symbol right here is mu. We've talked about him before, but he's like a scripted U. He is called mu, and he is similar to like X bar, which is what we use for the average. It's just that mu is what we use for a population. So let's say the population, I did not flip any more coins than just those 4 or whatever. This is talking about the population of all coins, okay? You know, when we're looking at all outcomes of coins, I guess I should say. Mu is the symbol that we use because we're talking about the population of all outcomes of coins, okay? This guy means the sum of all the x's times the p of x's. So if I go over here and I take x's, these are my x's, x times p of x, 0 times 0.25 is going to be 0. If I take 1 times 0.5, that is just 0.5. If I take 2 times 0.25, that is 0.5. And over here, when it says x times p of x, we just did those. We did x times p of x, x times p of x, x times p of x. And we need to take the sum of those. That's going to give me my average. Okay, so if I sum these 3 numbers all together, that gives me 1. So mu in this case is 1. And that should make sense. They're saying when I toss 2 coins, what's the average number of heads I should get? I should get 1 head, right? Like 1 head out of the 2 coins, the other being tails. That makes sense that would be my average. So mu in that case is 1, okay? And then they want me to do the variance and the standard deviation, which they're going to have us do. Oh, shoot. They gave us room down here. Whatever. They're going to have us do the variance and the standard deviation down here at the bottom. Okay, so we just did. Oh, I wrote it at the top. I'm sorry. 0 times 0.25 is 0.25. 1 times 0.5 is 0.5. 2 times 0.25 is 0.5. And if I add those all together and I do the sum, that is 1. So my mu, which is this formula, is 1. Okay? All right, now they want us to do, there's 2 formulas for doing the variance. And they, let's see, down here, they are having you do the top one. They're having you do the top one, okay, for some reason. I don't know. They say that one's the easiest one. I don't know. Whatever. But the standard deviation, I'm going to get rid of this and say, instead of using the formula, the standard deviation is just the square root of the variance. So whether you use this formula for variance or this formula for variance, the square root of the variance, the square root of either of those numbers is going to give you the standard deviation. Okay, so that's what we're going to do here. We're going to find sigma squared. That's the symbol that we use. Sigma squared is going to be my variance, and then I'm going to go down here and I'm going to say just sigma, which is the standard deviation. Variance. And we're going to find each one of those, okay? All right, so we found the average, and we want to find the standard deviation now. So this formula is what I use. I take x, okay? X is this 0. So I'm going to start by taking 0, and I'm going to subtract mu, and mu in this case is 1. I use this mu from before. And I take that value and I square it, and then I take that times p of x, which in this case is 0.25. Okay, I'm going to do that first, okay? 0 minus 1 is -1, and -1 squared is 1. and 1 times 0.25 is just 0.25. So that's what I get for this top one, okay? All right, then I'm going to go down and do the next one. So I'm going to do x again, but this time my x is 1. So I have 1 minus mu. The average is still 0, so 1 squared times p of x, which is 0.5. Okay, 1 minus 1 is 0. 0 squared is 0, and 0 times 0.5 is 0. So I have that. Okay, the next one, the last one, x for my last one is 2, and 2 minus the mean, or the average, is 1 squared times, this time my p of x is 0.25 again. So I'm going to do times 0.25. I don't know why I put him in parentheses, whatever. 2 minus 1 is 1. 1 squared is 1. 1 times 0.25 is 0.25. Okay, and then for the variance, they want me to take the sum of those guys. So I've already done the work, and I just want to take the sum. If I add those three numbers together, I get 0.5. So my variance is 0.5. Okay, hopefully that made a little bit of sense. And then for the standard deviation, I want to take the square root of 0.5, which is not 0.25. That's dividing by 2. That's different, okay? The square root of 0.5 is not the same thing as 0.25. The square root of 0.5 is, I knew that, 0.707. That's what my standard deviation is. Okay, now this is confusing for people sometimes, and I want to address this really quick. Normally your variance is larger than your standard deviation, right? Because you take the square root. But when you have numbers that are less than 1, as in like decimal numbers, when you take the square root of a decimal, you get a larger number. Okay, so that's a little bit hard for people to wrap their brains around. When you take the square root of a decimal or a fraction like 1/2 or 1/3 or 3/4 or something like that, when you take the square root, you actually end up with a larger number. Okay, that's only for numbers that are less than 1. Okay, numbers greater than 0, less than 1. Taking the square root will end up with a larger number for standard deviation. Okay, so normally it's not the case. You take the square root, you end up with a smaller number. Okay, but for this chance we do. Okay, so my standard deviation was 0.707. All right, now we're going to talk about in the next example what's considered to be significant and not significant. Okay, so I know we've talked about this before. When you have your average, if you add the standard deviation twice, that's the cutoff mark for what's considered significantly high. If you subtract it twice, the cutoff mark for significantly low is 2 standard deviations lower, right? So if my average is an 85 on a test and the standard deviation is 5, right? So mu is 85, the standard deviation is 5. That means significantly high values would be a 95 because I've added it twice. Significantly low values would be anything that scored less than a 75. Okay, so that's kind of how that breaks down. High values, low values. All right, now this is going to be a little bit confusing on example 4, but let's just bear with me, okay? So here it said my average was 1. This is what we just calculated from the table. My average was 1, and my standard deviation was 0.7. That's what we just got up here, right? Average was 1, standard deviation was 0.7. Like, we legit got those results, okay? So let me go ahead and fill out my bar here. My average was 1, and if I add the standard deviation twice, I get 0.7 plus another 0.7. That's 1.4 total, so 2.4, okay? 2.4 is my cutoff mark. Anything above 2.4 is considered significantly high, okay? If I subtract 0.7 and subtract 0.7, that's subtracting 1.4, or it would be negative 0.4. Okay, so let me break this down for you. These are significantly low values. Okay, anything that's considered above 2.4 is a significantly high value, and anything below negative 0.4 is a significantly low number. Okay, but let's think about what we're talking about. We are talking about flipping 2 coins, right? We're flipping 2 coins, and we're talking about the number of heads that show up when I flip 2 coins. Okay, So anything larger than 2.4 heads is going to be significantly high. But I'm only flipping it twice. Like, I'm never going to get 2.4 heads, right? That means I won't, in this scenario, I won't have a significantly high number of heads, right? Like, if you flip a coin twice and both of them come up heads, you're not going to be like, holy cow, wow, I can't believe they both came up heads. No, it's not a significantly high number. You're not going to get a significantly high number of heads if you're only flipping it twice, right? Anything larger than 2.4, that's not even possible, right? A significantly low number of heads would be negative 0.4, which we can't achieve either, because if we flip the coin and we got 0 heads to show up, you wouldn't be like, holy cow, I can't believe I got no heads to show up if I flipped the coin twice. No, you're only flipping it twice. Like, I can't believe that, like, in this case, our significantly high and our significantly low don't make any sense, so we don't have any significantly high, significantly low values when we're flipping 2 coins, okay? Now you might be like, well, why did they do that then? Why did they even have us find that? Because you will at some point run into a scenario where you won't have a significantly low value, but you will have one that's high, right? Or you will have one that's high, or you will have one that's low, but not one that's high, right? So they wanted to show this example to show you that, like, sometimes the significantly high, significantly low values won't make any sense. Like, you cannot have a negative number of heads. Like, that's not even a thing. I think maybe we've had one like that before, where we had a negative and you couldn't go all the way down. I don't know. I want to say we've had a problem like this already before. But anyway, just to show you, that's how this works out in this case. Okay, so with 2 coin flips, there is not a significantly high number. If we were flipping it 10 times, you might say, okay, anything greater than 8 heads in a row out of 10 coin flips is going to be a significantly high number. That's going to be okay. But with 2 coin flips, you don't really have any significant values because you're only flipping it twice. Okay? All right, hopefully that made sense. Okay. Also, if we don't have the standard deviation and don't have the values for the mean and the standard deviation, they might give you instead like the percentage of it happening, like the percent chance of it happening. And I know we've done this before. Anything that's less than 5% chance of happening is considered a significantly low or a significantly high number of whatever, right? So if it happens less than 5% of the time, it might be a significantly high number of heads or a significantly low number of tails, right? And that's how that works. Okay, so they did that in example 5. They're saying you are tossing a coin 460 times and they got 252 heads to come up. Okay, what does the result suggest about this, which includes the results from 460 overtime games? So we're talking about them winning the coin toss. Okay, so they're getting the coin toss to come up heads 252 times. When we're playing an overtime game, they have to flip the coin. Okay, so among 460 teams that won the coin toss, 252 of them won the game. Is 252 wins considered a significantly high number? Okay, they went ahead and calculated this out for me. We don't know how to calculate this yet. Okay, we don't know the formula yet, and that's okay. They're giving me this information. They're saying out of 460 coin tosses, 252 being a result for wins happens 2.24% of the time. So yes, 252 wins is considered, 252 wins of the coin toss is considered to be a significantly high number because it's only happening 2% of the time. Okay, they've done a little bell curve out here. 230 would have been average, right? 460 games, I should have 230 result in heads, 230 result in tails, but I've got 249, which is considered to be beyond, on the extreme end of things. That is only happening 2.24% of the time. Okay, they gave me those numbers because that's less than 5% of the time. It is considered to be a significantly high number of coin tosses resulting in heads. Okay, so hopefully that made sense. Yes, 252 out of 460 is significantly high. Okay, so there's that. right? If you don't have your mean and standard deviation, they might tell you this happens 2% of the time. Well, that means it's a significant number, right? So there is that. We are going to wait to do part 2 tomorrow, and you should be able to. So you should have 1, 2, and 3 hopefully done at this point. And then you should be able to do number 1 and number 2 tomorrow. You might get a little confused when it comes to part C on number 2, but just look at it, take it into consideration, see what it is they're asking, and then we can go over that tomorrow. Save number 3 for after we do part 2. Okay, so that should give you a little bit of stuff to do for today. Get that done for tomorrow.